I'd like to talk a little bit about our speaker tonight. Dr. Rob Jedicke, I know many of you have had the honor of meeting him. What you may not know is he's had 4 different careers in his short lifetime. He was a football player for the BC Lions. He was a particle physicist, a software engineer, and an astronomer. He started out playing as a pro football player, playing with the BC Lions, until he got cut. So he did what most pro football players do after they get cut. He went back to school for his PhD. And he did get his PhD, earn his PhD in experimental particle physics from the University of Toronto. Then he went to the University of Arizona, and then he worked as for a private company writing computer software. Then he joined IFA in 2003. Here he is the manager of Pan-STARRS Moving Object Processing Systems, which will discover more asteroids and comets in 1 month than have been found in the past 2 centuries. He has discovered 2 comets and an asteroid that has his family name attached to it now. You know, Canadians are a little bit different. I'm not meaning to offend anyone, but they have sort of a special connection with Santa Claus. I guess it's that cold air and frigid weather that they get used to or something. But maybe they see themselves as Santa's helpers. But Dr. Jedicke did really get special consideration when he was able to find out the secret knowledge about how Santa can get around and the extraordinary reindeer speed while he was studying particle physics. And with this, I am very happy and honored to introduce you to a very talented Canadian with special powers with Santa. Here is Rob Jedicke.
All right, thank you very much for that introduction, Donna. I'm very happy to be here. I gave this talk last year once. Of course, I can only do this talk once a year, right? Or at least one season in the year. And I gave this talk last year, and I gave it last week twice. I gave it once in Tucson and in Los Angeles, but I'm really happy to be here giving it again in Hawaii, because here nobody looks twice at you if you wear your slippers when you're giving a talk. So the point of today's talk is to try and determine whether or not Santa Claus needs to break the laws of physics in order to deliver all his gifts to all the people around the world. Is Santa Claus guilty of breaking the rules of physics? Now, in order to answer this question, first of all, we want to know whether or not Santa Claus is real. So what I did is what we all do nowadays, is I went online. You know, is Santa Claus real? Is anybody else kind of cold? Because I'm kind of cold. I think I need to wear on this hat now. This doesn't mean that I'm endorsing, you know, Santa Claus or Einstein. I'm just a little bit cold right here. So is Santa Claus real? You can go online and you can find this really great website called ask500people.com. And you can ask any question you want, and 500 people around the world, up to 500 people around the world, will answer your question. So I went in and I typed in, is Santa Claus real? And you can see that I got a lot of people answering from North America and actually a few people from the rest of the world. And you can look at these results in the overall, and you find out that 42% of people responding to the survey believe in Santa Claus, and 58% do not. And I think that's pretty optimistic. People actually believe in Santa Claus at that kind of level. Now, you can break results down by country, and I don't expect you to look at the results there by country exactly, but what I did is I chose the 2 most important countries, the United States and Canada, and we can compare the results from those 2 countries. In the United States, 28% of people believed in Santa Claus, but in Canada, fully 43% of people believed in Santa Claus. Now, as Donna pointed out, this is maybe sort of natural, because Canadians don't really think anything's unusual about living up in the north where it's cold and there's lots of snow on the ground all the time. We think nothing of big guys walking around in funny hats and red jackets and crazy-looking boots. Except we call them the Royal Canadian Mounted Police. Now, there's another way we can look at these results, and we can split it up by a country's religion. And it's very interesting. If you look at those results by the people who live in Christian countries versus people who live in non-Christian countries, only 38% of Christian country respondents believe in Santa Claus, whereas in non-Christian countries, 61% of people believe in Santa Claus. So I think this is actually very important, because when we want to know whether or not Santa Claus is breaking the rules of physics, we know that he's delivering all his gifts to everybody in the world, not just the good Christian children. So now we've talked a little bit about whether Santa Claus is real. Let's talk about the origins of Santa Claus. Santa Claus is thought to, the myth of Santa Claus, or the story of Santa Claus, is thought to be based upon the Saint Nicholas of Myra, who was a 4th century AD saint. He was apparently a very wonderful man who devoted his life to Christianity, and also quite wealthy. There was one peasant who had 4 beautiful daughters, and this Saint Nicholas of Myra donated a large amount of money to this peasant so that he could provide dowries to each one of his 4 daughters so they didn't have to become prostitutes. So in honor of the fact that he donated so much of his money to this poor peasant, he is now the patron saint of children. Makes a lot of sense. Interestingly enough, he's also the patron saint of lawyers. I really don't see the connection there. And even more so, and maybe relevant to the story, you see that St. Nicholas is also the patron saint of prostitutes. So an interesting mix for this particular saint here. So it's a wonderful heritage that Santa Claus is actually being derived from. So now the modern origins of Santa Claus can be traced back to 1823, to this particular poem, "'Twas the Night Before Christmas." I'm sure we've all read it and enjoyed it very many times. But this poem alone is responsible for our ideas of what Santa Claus is, in terms of the reindeer, in terms of him coming down the chimney, all those different things. It was this particular poem less than 200 years ago that defines our idea of Christmas. The first image of Santa Claus didn't arise until 1863 on the covers of Harper's Weekly magazine. You can see him there on top of some sort of a sled. But our real modern image, view of what Santa Claus actually looks like, was really formed by the Coca-Cola Company in the early 20th century. It was this particular image of Santa Claus that really formulated our ideas of Santa Claus having a white beard and a red hat and a red jacket. And I always think this is kind of funny because basically Coca-Cola, probably unilaterally without Santa Claus's permission, is using his image to sell their product. And I think that the lawyers who have the patron saint of St. Nicholas should be suing Coca-Cola to get all the money to pay for the poor children in the world to deliver the gifts. Now, so that's the origins of Santa Claus. What about the origins of Einstein? Einstein was born in the late 19th century to Pauline and Hermann Einstein. I can't imagine how proud they must have been when they grew up. You know, nowadays parents get these bumper stickers that say, you know, my kid's an honor student at Punahou or whatever. And if these two people had that kind of tradition, they could have a bumper sticker that says, my son was person of the century. In 1999, he was voted Person of the Century by Time magazine for the contributions that he made to physics. So let's start talking about how fast Santa Claus goes, because whether or not Santa Claus breaks the rules of physics all depends on how fast he's actually moving. Now, I promised in my abstract for this talk, if you went online or you saw this in the newspaper, that this was going to be an equation-free presentation. And I'll be straight with you, I lied. There's actually 2 equations in this presentation, but they're all on this sort of scale, so don't get intimidated by the equations. So whether or not Santa Claus breaks the rules of physics depends entirely on how fast he's going. If he's going too fast, then he's going to break the laws of physics. If he's going slow, then it doesn't really matter. So this equation is critical to determining whether or not Santa Claus is guilty of breaking the laws of physics. So let's break this equation down. Speed, how fast you're moving, is simply the distance that you travel divided by the time. If you go 60 miles in 1 hour, you're going 60 miles per hour. Very simple. Let's look at Santa Claus's problem, and let's look at just the top part of that equation, the distance that Santa Claus needs to travel. Now, this is a very interesting question. First of all, we need to know how many people live in the world. All right? When I was born, back in 1963, the population of the world was just a little over 3 billion. Nowadays, approaching 2010, the population has doubled. The population of the world has doubled just in my lifetime. I find that really incredible. But the problem really isn't that complicated for Santa Claus, because Santa Claus only has to deliver his gifts to the good people of the world, right? The good children. So, you know, when I was a kid, lots of children were well behaved. We listened to our teachers. We did what our parents told us to do. But the problem is that even though the world's population has been increasing, the population of good children in the world is not increasing that fast. So we all know that children nowadays are not nearly as well behaved as they were in the past. So Santa Claus's problem is a little bit easier than it was 40 years ago. Now, let's look at how he visits all those different people. It's an interesting question in mathematics or computational science known as the traveling salesman problem. Santa Claus has to visit a huge number of cities, a huge number of homes within each city around the world. How does he actually do that in a very efficient way so that he saves the wear and tear on his reindeer and the wear and tear on his sled? It's an interesting problem, and let's consider a very simple situation. Let's consider just 60 cities it has to visit. So each one of these blue little stars here represents a single city, and let's say that you were very stupid and you just connected all the cities sort of randomly, you'd have a very inefficient path to get around to those different cities. Now, if you're actually a salesman, you want to make sure that you are being as efficient as possible for your company. You want to minimize the amount of gas that you're spending. You want to minimize the wear and tear on your car. You want to minimize the amount of time that you're spending traveling around so that you can get back to your family. So this is not an efficient way to travel around to these 60 different cities. Instead, you can connect the dots in a slightly different way, and you can run a computer program to figure this out, and you can find the most efficient way to get around to those cities. Now, when you've only got 60 different cities, or maybe 100, or maybe around 200 or so, computers nowadays are so fast and so powerful that they can actually solve this problem exactly. You can give a list of 100 different cities, and you can type them into the computer and tell them exactly where they're located, and the computer can search through every single possible combination and find what the fastest route is between those cities, and can solve the problem exactly. But once the problem gets a little bit more complicated, once you get above a few hundred cities, once you get up into the thousands or more, the problem becomes very complicated. If there's a 3,038 city tour, the number of possible routes between all those 3,038 cities is this. Okay? This is one number. Okay? You've probably never seen a number written down this big, right? This is, wait a second here, I think I made a mistake right here. Of course, this is just ridiculous, right? It's a ridiculously huge number, and computer programs can no longer solve this problem exactly when you have thousands of cities that you have to visit. Instead, they sort of develop some sort of approximations to the fastest route to the different cities. And even though they can't know exactly when they found the right solution, they can measure how close they are to the right solution. And they know that this particular, when they solve this problem through the computer, they know that they can get within a fraction of a percent of the most efficient distance between all the different cities. So the point is that you may not know the exact best route through the different cities, but you can get a very, very close approximation. Now, Santa Claus's problem is a lot more difficult than just 3,038 cities. If you go to an index of cities and villages and crossroads in the world, there's roughly 1.9 little villages that 1.9 million that Santa Claus has to visit around the world. And you can see that this is little tiny places in the middle of the ocean and up in the northern Arctic in Canada and Siberia, in the middle of the Sahara Desert and the Australian outback. This is a very comprehensive list of all the cities in the world, and Santa Claus has to visit each single one of them. If you actually try and run this data through a computer to find out what the most efficient route around the world is, it turns out that Santa Claus needs to travel about 4.7 million miles to get around the world. Now you can see this is the actual route solved by a computer. And again, it's not the exact perfect route, but it's very close. It's within a fraction of a percent of being the optimal route. And you can see that Santa Claus travels all around the world and hits all sorts of little towns and villages all across the world. He, of course, makes a jaunt up to Hawaii, hits each one of the different islands up there. And eventually he makes it all the way across into North America as North America comes across the horizon. So Santa Claus needs to travel 4.7 million miles just to visit the cities in the world. But within each city, he has to travel between the houses. Okay? And that actually turns out to be even a more complicated problem because there's many more houses than there are cities. We already know that there's about 7 billion people on the planet. And if you assume that there's roughly 5 people per household, that means that there's 1.4 billion households that Santa Claus needs to visit as he goes around the world. Now, that map that you see behind the text is a map of the population density of the world. And the thing that you can take away from that is that the population density within a city is about 1,000 people per square kilometer, or that's about 2,600 people per square mile. And if you work it out, and it's not that difficult, the math, but I didn't want to bore you with too many equations. If you work it out, there's approximately 2,600 people per square mile, and that means that the average distance between households is about 70 yards. Okay? So that means that over all the world, the average distance between households is 70 yards. And you think that inside of Honolulu, the average distance between households is much less than 70 yards, but you think on some place like the Big Island, there can be a large distance between households, and so it sort of averages out to about 70 yards between households. So if it's 70 yards between each household, and there's 1.4 billion households, that means that Santa Claus needs to travel 60 million miles just to get between the households within the cities. So let's review that. He travels about 4.7 million miles just to get between the cities. He travels 60 million miles between the houses within the city for a total distance of about 65 million miles, and he does this all in one night. Let's put that into perspective. 100,000 miles between the Earth and the Sun. Santa Claus has to travel 2/3 of the distance between the Earth and the Sun just in one particular night. And he somehow, obviously, finds a way to solve this problem exactly. And I think what this shows is that not only does Santa Claus have a major, massive toy production facility up in the North Pole, he has one honkin' big computer system. So let's look at the bottom part of that equation. Speed equals distance over time. Let's look at the time that Santa Claus has to go around the world. Well, it seems like it should be a simple problem, right? You put your kids to bed around 8 p.m., and they wake up at 6 a.m. all eager to open up the presents. It sounds like he's got 10 hours in order to deliver his presents. But that's just 10 hours in your particular time zone. But there's quite a few time zones around the planet. So let's try and think about how much time Santa Claus really has. So let's say that Santa Claus starts out at 8 p.m. on December 24th, on Christmas Eve, just on the western side of the international date line. And then he basically continues heading westward, chasing the sunrise, until he reaches the eastern side of the international date line at 6 a.m. on Christmas morning. And if you work that all out, it turns out that Santa Claus has got 34 hours to travel around the planet. So he's got to go that 65 million miles in 34 hours. Now that, if you work it out, is just about 2 million miles per hour. Okay? Now, you're all laughing because you think that sounds very fast, right? But to a physicist just scoffs at the kind of speed. That's nothing, okay? And let me tell you why it's nothing. It's because the speed of light is 1 billion miles per hour. So Santa Claus only has to move at 2 million miles per hour in order to deliver all his gifts. But the speed of light, which I always represent by the letter C up there in the upper left-hand corner, so C will always represent the speed of light. Speed of light is 1 billion miles per hour. So let's put that speed that Santa Claus has to travel at into perspective. Oh, sorry, let's first of all talk about how big 1 billion is, because 1 billion is a huge number, right? It's a number that human beings have a lot of trouble conceiving of. I read somewhere once that human beings have trouble conceiving of any number larger than 8, okay? And what they mean is that basically if you throw like a package of toothpicks, right, and you ask people to estimate how many toothpicks there are, they are always wildly wrong on their estimate. They just cannot conceive of a large number of objects. So human beings have no way to understand how big 1 billion is. So let's think about one human being on the planet who mightn't actually know how big 1 billion is. And I think you can all figure out it's Bill Gates. Bill Gates may actually know how big 1 billion is. He will know how much $1 billion buys you. Okay? So let's ask Bill Gates for $1 billion bills. Okay? Not just $1 billion in $100 bills, but 1 billion $1 bills. And let's see what we can do with it. Let's say that we had an army of people and we distributed those $1 billion bills to each one of them. And we said, okay, what we want to do is we want to form a line of dollar bills around the equator of the Earth. So we're going to lay down $1 bill, and then we're going to lay them end to end and see how far that line goes. In your head right now, think about how far you think that's going to go. Well, actually, that line of dollar bills will go 4 times around the entire Earth. Okay? So 1 billion is a huge number. $1 billion bills extends 4 times around the equator of the Earth. Another way to look at it is, let's say we stack the dollar bills on top of one another. So we just take them, we just stack them up. Well, a stack of $1 billion would be 60 miles high. Okay? Now, to put that in perspective, Mount Everest, the tallest mountain above sea level on our planet, is only 6 miles high. So a stack of $1 billion bills is 10 times higher than Mount Everest. Another way to look at it is that the International Space Station orbits the Earth only 210 miles above the surface. So it would only take $3 billion bills to create a stack that would reach the space station, which interestingly enough is less than the space station costs. So let's look at this. Let's look at the minimum speed that Santa Claus has to travel at now in terms of the speed of light. He only needs to move at 0.2% of the speed of light. That's nothing. To a physicist, 0.2% of the speed of light is just nothing. It's not a problem at all. There's no way that Santa Claus needs to break the laws of physics. But in fact, it's a much more complicated problem than that, right? Because Santa Claus is not just traveling all the time. He's doing a whole bunch of other things. Santa Claus has to stop his sleigh, enter the chimney, distribute gifts, eat milk and cookies, exit the chimney, start the sleigh up, and he's got to travel at the same time. Now, I think it's pretty clear. We all, as children, left out milk and cookies for Santa Claus, and we all know that Santa Claus always ate the milk and cookies. So he's taking a lot of time eating those milk and cookies, and just based on his size, we know that he enjoys it. So what I did in trying to figure out how fast Santa Claus has to move is I assigned a lot of time for Santa Claus to eat the milk and cookies, and then just a little bit of time to do all those other things. And I gave him the minimum amount of time that I could think of to travel between the cities and between houses within a city. So I gave him 25 seconds to travel between all the cities, 325 seconds to travel between the houses, meaning that he travels 65 million miles in just 350 seconds. Now, if you work that out, that works out to 186,282 miles per second, and that is 99.999% of the speed of light. Now, gets interesting, because when you start moving at very close to the speed of light, strange things start to happen. Physicists call this relativistic travel. Now, relativistic sounds very complicated, but in fact is not complicated at all. All relativistic means is that you're moving at a speed that's very, very close to the speed of light. And when you do that, crazy things start to happen, crazy things to human beings. So relativity is basically the study of what happens when you move very fast, when you move at speeds that are close to the speed of light. This etching that you see here is from Escher. It's actually titled Relativity, and you can see that how you look at this house and how you look at the people inside of it depends upon how you're looking at it. So depending on who you're looking at, you see windows and doors sort of changing places. You see people standing upside down on different walls. And that's kind of what happens in relativity. Relativity switches everything around. It changes things around from the way human beings are normally used to looking at things. In fact, relativity, when you're moving very, very close to the speed of light, changes things that we consider very fundamental, things like time, speed, and mass. You know, we think that time moves at one particular rate, and time is always moving at that rate. We think that speed, you know, if you measure somebody's speed and then somebody else goes and measures that other person's speed, you always get exactly the same answer. And you think that mass seems like a very intrinsic property of an object or a person. And how can mass possibly change? But in fact, when you're moving at very high speeds, very close to the speed of light, all these things become much more fluid. And we don't understand it. We really have a trouble comprehending how this can possibly happen, because we live in a very low energy, low gravitational field, low speed environment. If we were beings that somehow could travel at the speed of light all the time, we would not think that these things were unusual at all. We would think it was unusual and very boring to be living on the Earth, because on the Earth, all these things are constant and they're not very much fun at all. If you move close to the speed of light, things change. So I kind of look at it as, you know, if you grew up here in North America and you look at people who are in China and they eat with chopsticks, and you say, well, wow, why would they do that? And why is it so different? Well, you know, if you grew up in China, you would think it was perfectly natural to be eating with chopsticks. And here we think it's perfectly natural to eat with a knife and a fork. But, so it's all relative, right? How you perceive the world, how you perceive the universe is all relative to where you grew up, and in particular, is relative to how fast you move and how much energy you have in your environment. So a lot of times as I'm going through the rest of this talk, you're going to ask to yourself, why does it happen that way? Okay, why do these things happen? Why does time, speed, and mass actually change? And the answer, very simply, is because nothing can travel faster than light in a vacuum. So that's really the only answer. You know, you can say, why does it happen? Why does the universe work that way? And I'm going to say that it's just because nothing can travel faster than light. That one assumption makes everything else in relativity happen the way it does. Now, then you're going to say to me, why can't anything travel faster than light? And I'll tell you that that's just because that's how the universe works, right? Is that you just have to accept that the universe is built such that the speed of light is the maximum speed you can possibly travel at. And it reminds me of a story of an American philosopher who was traveling through India, and he met an Indian mystic. And the American philosopher said, well, I understand that in Indian mysticism, the earth is a flat sheet with four corners, and each of the four corners rests on the back of a large white elephant. And the American philosopher says to the Indian mystic, so what do the four white elephants stand on? And the mystic says, well, they stand on the back of one even larger white elephant. And the American says, well, that's really great. What does that one big white elephant stand on? And the guy says, well, it stands on the backs of four other large white elephants. And the American philosopher says, okay, and so, you know, what do they stand on? And the Indian mystic says, it's white elephants all the way down. Okay? And that's kind of the point I'm trying to get here. This is the ultimate answer. Light, nothing can travel faster than light. That is the way the universe works. That is why all these strange things happen. So, let's move on. Let's talk about some of the origins of the theory of relativity. Let's think about waves, okay? Now, we all know what water waves are. Many of us probably surf. Many of us enjoy the ocean even if we don't surf. Well, water waves, ocean waves, travel on water. So there's a wave, and it actually travels in something. It requires water. If there were no water, you can't have ocean waves, right? They're kind of intimately linked. Think about sound waves. Okay, sound waves, we probably all know this, that the sound that's coming out of my voice that's produced by my vocal cords, travels through air in little density variations in the air, travels through the air to your ear, where your eardrum picks it up and your brain interprets it as my voice. So sound waves require air to travel. If we were in outer space, and where there's no air at all, sound would not travel at all. It's kind of like these things you see in Star Trek where there's a big giant explosion and there's a big sound that they hear. You know, that could never possibly happen because there's no air in space. A little more esoterically, the seismic waves actually travel through the Earth, through ground. Seismic waves require the Earth to actually travel through. So all these different types of waves have got some kind of a medium in which they travel. What about light waves? Okay, light waves seem to travel through almost anything, right? Light waves travel through air. These lights are shining on me. The light from the screen is shining on you. Light waves can travel through solids. They can travel through glass and your diamond ring, for instance. And light waves apparently can also travel through space. They can get from the sun to the Earth. And I just said that there's absolutely nothing between the space and the Earth. It's a vacuum. There's no air. There's no nothing between the Earth and the sun. So how do light waves possibly do that? Why do all other waves require some kind of medium to travel through, but light apparently doesn't seem to? Now, this is a really big problem back in the 1800s. In the 1800s, physicists really had to question what was going on, because all the waves that they knew of, all the mathematics that they knew that could describe how waves travel, all required that there be a medium in which the wave traveled. And so what the scientists back in the 18th century did, or sorry, in the 1800s did, is they basically invented something that they call the luminiferous ether, okay? And they just hypothesized that this luminiferous ether filled the entire universe. It was very evenly spread out, and it had extremely amazing properties. It was very, very difficult to detect, but it had exactly the right properties to allow light waves to travel through it. Now, you may think this sounds very strange, that the scientists just made this stuff up, right? But in fact, scientists do this all the time. Scientists are always making stuff up. The thing about scientists is that once you go and you make something up, other scientists come and try and disprove your theory. So some scientists came up with this idea of luminiferous ether, then other scientists came along and they tried to find out whether or not the luminiferous ether actually existed. So how do they actually do that? Well, let's consider the case of, before we move there, let's think about if you are on a, let's say you've got two friends. One of them is standing in the back, driving a truck. One of them standing on the back of the truck wearing a catcher's mitt, and you've got a baseball, okay? And so if the person in the back of the pickup truck that's got the catcher's mitt is moving away from you in the car, and you throw a pitch at them at 100 miles an hour, and the car is moving away from you at 50 miles an hour, then the speed that the catcher is going to catch the ball at is going to be 50 miles an hour. Alternatively, if the driver is driving straight at you at 50 miles an hour, and you throw a pitch at the guy in the back at 100 miles an hour, then the speed that the ball is going to hit the mitt at is going to be 150 miles an hour. And finally, if the person is driving sort of perpendicular to your line of sight, and you throw the ball at them, and the person is just going across your line of sight and catches the ball, then the speed that the ball is going to hit the mitt at is going to be exactly 100 miles per hour. Well, we can look at this actually the same kind of situation with light. Let's say that you're on the surface of the Earth, and you're looking at a very distant star that's, say, way up there on the upper left part of the screen. And in this particular case, the Earth is moving around the sun, and at that particular instant, when you're looking at the star, the Earth is moving in the direction towards the star, okay? So now you've got light coming at you from the very distant star, and you're moving on the Earth towards the light beam. So you would think that in that particular case, you would measure a speed of light that is quite a bit faster than normal. Now, on the opposite side of the sun, the Earth is moving in the opposite direction. So in this particular case, the Earth is moving away from that very distant star. So in this particular case, it's like your friend in the pickup truck driving away from you. And when you measure the speed of light, you're going to measure a very small speed for the light beam. And finally, when the Earth is in that particular location, the velocity of the Earth is perpendicular to the direction towards the star, and the speed of light that you're going to measure will be just the exact speed of light. So this, if you were to measure the speed of light from that particular star as you go around the sun, you would see the speed of light changing in a very regular pattern. So what happened was these two scientists came up with this idea of actually trying to measure the speed of light in different directions. And they developed this particular experiment. Now, I think this is really amazing because this is before laser beams. This is before computers. Right? This is before all the modern technology that we have to try and do these kind of experiments. But these guys came up with this fantastic experiment. They had a pool of, they built this experiment on in the basement of a building, so that the basement of the building is lying on solid rock. There's no swaying of the building or anything like that involved. And then they have this large pool of mercury, right here, pool of mercury, on top of which this huge slab of granite floats. So you're on the basement floor of a building, so it's very, very stable. Plus you've got this very stable mercury that's floating, and then you've got this huge, massive granite block that's floating in the mercury. And on top of that large granite block, they have a light source here, and the light source has just a pinhole light in it. There's no laser beam. The light comes out of the pinhole, and it passes either through or bounces off of something called a half-silvered mirror. A half-silvered mirror is exactly what you'd think. It's got 50% of the silver on it, so that 50% of the light goes straight through, and 50% of the light bounces off. And then the light bounces that goes straight through, bounces off this mirror, bounces back here, and finally bounces here into this telescope or a light detector, you can think of it. Similarly, the light that went down this direction bounces straight back here and into this detector right here. Now it turns out, and I won't get into too much detail here, that this particular instrument allows you to measure the speed of light in both of those directions. Okay, so you can measure the speed of light in this axis and on that axis. So if you line this particular instrument, one of the axes with the direction of motion of the Earth, then you can measure the speed of light in the direction of motion of the Earth and in the perpendicular direction. And similarly, because you can rotate the granite slab around on the pool of mercury, you can measure the speed of light moving in the opposite direction when the Earth is on the opposite side of the Earth, or opposite side of the sun, and you can rotate the whole instrument around to measure the speed of light. So these guys basically measure the speed of light in two different directions, perpendicular and parallel to the direction of motion of the Earth relative to the sun. And what they found was that the speed of light did not appear to change. No matter how they measured the speed of light, no matter what direction they tried to look at the speed of light, no matter what time of year they were looking at, they could not see any change in the velocity of the speed of light. This experiment is now known as the Michelson-Morley experiment. It's also known as the greatest experiment that ever failed. Right? They went out to try and show that they could measure the speed of light in different directions and show that the luminiferous ether actually existed. Instead, what they showed is they could not see any difference in the speed of light. And that implied that the luminiferous ether did not exist. But if the luminiferous ether did not exist, then how could light possibly travel between the sun and the Earth? Well, it took Einstein's genius and about 30 years before anybody realized what the experiment meant. Everybody else, a bunch of other scientists came along. They tried to redo the experiment. They didn't believe that Michelson and Morley had done it correctly. They thought that there were errors. They did it with higher sensitivity. Basically, nobody could ever show that there was actually a change in the speed of light depending on what direction you were looking. So Einstein's brilliance was that he was willing to accept the results of this experiment at face value. Einstein said, okay, let's accept that there's a universal speed limit of the speed of light, about 1 billion miles per hour, and that nothing in the universe can ever travel faster than the speed of light. And furthermore, that light is always traveling at that speed in a vacuum. So if you always measure the speed of light in a vacuum, it's always going to be moving at that speed. So this is a really incredible mental feat, and to think that somebody could actually come up with this idea, because it's very contrary to how we would think. We would think that the speed of something always has to change depending upon how you look at it. But Einstein said, no, let's just assume that the speed of light is constant regardless of the motion of the observer. So the fact that the speed of light is constant introduces the effects of relativity, and I want to describe for you now 3 different effects of relativity that are extremely bizarre. First of all, let's talk about faster than light travel. Now, and how we know it's true. Now, you may think this is very strange because I'm talking about the speed of light being a universal speed limit, nothing going faster than the speed of light. But actually, there's sort of a catch here. The common definition of the speed of light is that nothing can travel faster than the speed of light. But that's not exactly correct. A more correct definition is that the information cannot be transmitted faster than the speed of light in a vacuum, which is 186,282.397 miles per second. Now, that may be a very subtle difference to you, but it actually has some major implications. For instance, the speed of light in a diamond is only 40% of the speed of light in a vacuum. So when you look at light coming out of your diamond, the light, when it was in the diamond, was actually moving at only 40% of its speed in a vacuum. It's only moving at 75,000 miles per second compared to 186,000 miles per second. So light slows down when it goes through different materials. That's very important to keep in mind. Now, I'm going to diverge a little bit here into my particle physics, put my particle physics hat on, and let's talk a little bit about what the atom actually looks like. I need to introduce some concepts here in order to describe how we know things actually can travel faster than light. So an atom, I like to think of it as a big fuzzy blob. Many of you have probably seen pictures of it where there's something in the center and things orbiting around it, but I like to think of it as a big fuzzy blob. And that fuzzy blob is about 10 to the minus 10 meters in diameter. Now, I personally hate it when scientists put up crazy units like 10 to the minus 10 and meters that nobody understands. So let's put that in units we all know, 0.0000009 inches across, right? Now that's kind of ridiculous, so let's put it into perspective. Let's blow up one human hair. Think about how fine, how thin your hair is, okay? And this is one human hair blown up and displayed here on the screen. It would take 1 million atoms to cross one human hair. Okay, so that's how tiny an atom is. Now keep that in mind as I keep talking about the atom. So let's look at the atom. The atom, this sort of fuzzy cloud that you see here, is actually made up of electrons. Now most pictures you've seen of atoms probably show all sorts of electrons zooming around in elliptical kinds of orbits. I personally do not like to look at an atom in that way, but I've done it like this in order to give you a perspective that you're probably used to. I like to think of the electrons just sort of being fuzzy clouds that sort of form the shape of the atom. Now an electron is a fundamental particle. An electron, there's nothing inside of an electron. Okay? An atom is composed of other things, but an electron is a fundamental particle. There's just nothing inside of an electron. An atom is a pure mathematical point in space. There's nothing, it has 0 dimension. Okay? That's kind of weird. Now, electrons emit something called photons. Photons can be thought of as light. Light can be seen as both as a wave or a particle, depending on how you're looking at it. So electrons emit photons, and photons are also fundamental particles. Now let's look at the very center of an atom. If you were to zoom into the atom, take in that little box right there, if you zoom in, you'd eventually get to something called the nucleus. Now the nucleus is tiny. We already established how big the atom is, right? How small the atom is. The nucleus, let's say that the atom was the size of a football field. Okay? The nucleus of an atom would be ½ an inch big on the center line. Okay? So the atom is stretched out to this whole size of a football field. The nucleus would be just ½ an inch big on the center line. Tiny, tiny little object. Now the nucleus itself is made up of something called protons and neutrons. And you might think that protons and neutrons were fundamental particles, that you'd actually got to the fundamental particles of which matter is made. But that's not exactly true. Let's blow up one of those protons. And if you look inside the proton, you see that's actually this kind of a cloud-like thing like the atom was. But inside that cloud, you'll find particles called quarks. In fact, a proton is made up of 2 quarks known as up quark and 1 down quark. And it doesn't matter too much about exactly how they interact or anything like that. But quarks are also fundamental particles. There's nothing inside of a quark. A quark has 0 dimensions, 0 size. Now quarks are held together by something called gluons. And gluons are represented by this kind of a squiggly little line like that. And gluons are also some of these fundamental particles. Now, these 5 particles that I've introduced here, the photon, the electron, the down quark, the gluon, and the up quark, are the fundamental particles of which everything you've ever known is made of. There's nothing else. Everything in this room, everything in the earth, everything in the universe is made up of those 5 different particles. And by combining them in different ways, you get different things. Okay, so gold, diamond, earth, human beings, they're just photons, electrons, up and down quarks, and gluons combined in different ways. These are the fundamental particles of all the universe. So let's talk now. Now I've given you an idea of what the atom looks like. Let's talk about what atomic fission happens. This is what happens in an atomic bomb. In an atomic bomb, you take something like a uranium atom. An uranium atom's got a nucleus that's made of protons and neutrons. One neutron comes into the uranium atom very fast, and it disrupts, it totally blows apart the nucleus of the uranium atom, creating 2 lighter elements, and also some spare neutrons and a lot of energy. Okay? So this is basically what happens in nuclear fission, in a nuclear bomb, and also in a nuclear reactor. Now let's put this in the context of a nuclear reactor. In a nuclear reactor, you have an atomic fuel rod made of uranium with all sorts of uranium atoms inside of it, and one of the uranium atoms splits apart and creates 2 lighter nuclei, and then these 2 neutrons here, and the 2 neutrons go off and they can interact with other atoms. These 2 lighter nuclei don't do much, but the energy that I was talking about gets taken away from the interaction in something by electrons. So these are these other fundamental particles. A whole bunch of electrons come out of this interaction in all sorts of different directions, and they take a lot of energy away. They have so much energy that they're moving very fast. In fact, these electrons are moving at 99% of the speed of light when they come out of that reaction. 99% of the speed of light. The crazy thing is that the speed of light in water is only 75% of the speed of light in a vacuum. So these electrons are actually moving faster than light in water. So there is something like faster than light travel, but it only can happen when you're traveling through a material, a medium. In this particular case, the electrons are moving faster than light. Now this is a very unnatural situation, and so the electrons try and break. And the way they break is by emitting radiation. In this particular case, the radiation is called Tranquil Radiation. And it's this beautiful blue light. And if you take a camera and place it inside of a nuclear reactor, you see this beautiful blue light from the Tranquil Radiation. Now I want to emphasize that this is not the inside of a nuclear reactor illuminated with a light. They just put a camera inside the nuclear reactor. There was no light. There's no external light, no cords going into the nuclear reactor with a light on. This is just the Tranquil radiation being emitted by the uranium in the core of the nuclear reactor and the electrons that are emitting the Tranquil radiation. And notice it's got this sort of beautiful blue and white glow to it. Now, you may wonder what all this has to do with Santa Claus. So let's bring it back. Let's look at this picture of Tranquil Santa. So the speed of light in air is 99.97% of the speed of light in a vacuum. But we've already established that Santa Claus moves at 99.9999% of the speed of light. Now that means that Santa's moving faster than light in air. And that means that he has to be emitting Tranquil radiation. Now if we look at this picture, okay, we see that it's got this beautiful blue and white glow all around it. Now I'm pretty sure that the artist who drew this did not know anything about particle physics or relativity, and that this then is probably an independent confirmation and an actual sighting of Santa Claus traveling at faster than the speed of light. So, evidence pointing towards Santa Claus being innocent? Yes. Let's look at a bizarre effect number 2, mass gain, and how we know it's true. So relativistic mass gain could be very complicated for Santa Claus because Santa Claus is already a large guy. Right? And if he's actually gaining mass when he's traveling, that could cause problems for him entering into chimneys and delivering all the gifts. So what I'm going to do is we're going to do a little thing called a thought experiment, what Einstein would have called a Gedanken experiment. Gedanken is German for thought. And so let's just see what this would happen. Let's just do a little experiment. So this is a Santa speedometer, okay? And basically this is an instrument that can measure the speed that Santa Claus hits the screen at, okay? And I'm going to toss him at the speed and toss him at the screen, and we'll see how fast Santa Claus moves, okay? So let's see here. Oh, 50%. Okay, so Santa Claus needs a reindeer to pick up himself. Okay, thank you very much. Whoa! Good throw. Can you wait there? We got to do some more here. So okay, so I didn't toss Santa Claus very fast there, right? So Santa Claus is this time I'm gonna actually try and give him a little bit more heat. So let's see what happens here. Oh, 90%, okay? So Santa Claus is moving at 90% speed. Now I gave him, here we go. All right. So I gave him a lot more energy, right? But he only increased his speed to 90% of the speed of light. So now I'm gonna try really hard. 99% of the speed of light, okay? So no matter how hard I'm throwing Santa Claus, thank you. No matter how hard I'm throwing Santa Claus, he just doesn't seem to be going faster. And one more time here, as hard as I can, 99.9% speed of light. So no matter how hard, how much energy I give Santa Claus, thank you very much. So no matter how much energy I gave Santa Claus, he increased his speed, but only by tiny little incremental fractions. He never, ever increased his speed above the speed of light. So what was happening to all that energy? So let's think about this equation. This is equation number 2. You've probably seen this before, the mass energy equivalence equation. And the C we already understand stands for the speed of light. E stands for energy, and M stands for mass. What this means is that energy and mass are equal to one another, except for this factor, the speed of light squared, the speed of light times itself. And it doesn't matter so much what this equation, how this equation actually works, but just think about the fact that energy and mass can be considered the same thing, and they can be sort of interchangeable with one another. Now, let's look at a particular reaction that is kind of common in the universe. It's called hydrogen fusion. And what happens in hydrogen fusion is that 4 hydrogen atoms come together, and they get squeezed together at very high speeds and very high temperatures to form 1 helium atom. The interesting thing is that 4 hydrogen atoms weigh more than 1 helium atom. So what happened to that mass? We take 4 hydrogen atoms, create 1 helium atom. Something happened to the mass. There's matter that's missing. Well, that missing matter is actually turned into energy. Okay? So here we've converted matter into energy. And somehow that doesn't seem so strange, right? Converting matter to energy. But it's extremely important. To boil 1 quart of water requires 100 quadrillion hydrogen fusion reactions just like that. Now that sounds like a lot of reactions, right? Except for the fact that each quart of water contains 70 septillion hydrogen atoms. Okay? So it only takes a tiny, tiny little fraction of all the water in a quart of water to boil that quart of water. Right? And if you take a lot more hydrogen atoms, and you get them going at the same time, creating hydrogen fusion, you create a hydrogen fusion bomb, which it releases a tremendous amount of energy. And in fact, in the center of the sun, what happens is 600 million tons of hydrogen get converted into 596 million tons of helium every single second of every single day for the last 4.5 billion years. So if you do the math there, 600 minus 596, you realize that 4 million tons of hydrogen get converted into pure energy every second in the sun. And all that power is what generates all the energy that we have on the surface of the Earth. Now, it's not so hard to think about energy, for mass being converted into energy. Somehow that seems like, okay, so the mass disappears, the mass has to go somewhere, it gets converted into energy. But converting energy into mass seems a little more strange. And I want to give you an example of how we actually know that this actually can take place. To do that, I need to tell you more about particle physics in a place that I used to work at called Fermilab. And Fermilab looks something like this when you draw a schematic for it. And I'm going to turn the map of Fermilab around so the maps actually match. Now, what happens at Fermilab, don't worry too much about the details, but what happens at Fermilab is we take protons, which I've already introduced, they're in the nucleus of an atom. We take individual protons and we spin them around in an accelerator. And every single time they go around this circle, they get a little bit more energy injected into them. And every time they get a little bit more energy injected into them, they move faster and faster and faster. When they're moving fast enough, at speeds very close to the speed of light, we take them out of the ring and we send them down these tubes. They're called beamlines. And at the end of the tubes, what we're really doing at the end of the tubes is we're really measuring the mass of the proton. So once again, we speed up the protons in the ring, injecting energy into them. We slam them down these tubes, and at the end of the tube, we measure the mass of the protons. So what actually happens is, at the very beginning, we put 2 units of energy into the proton. Now, it doesn't matter what these units are. These are million electron volts. It doesn't matter. Just think of this as 2 units of energy, and the proton is spinning around in that accelerator. And at that amount of energy, it's already moving at 87% of the speed of light. Now, if we increase the energy up to 10 units, the proton is then going to be moving at 99.5% of the speed of light. So we increased the energy by a factor of 5, and the speed only went up a tiny bit. Now we increase another factor 10, and the speed goes up more, up to 10,000 units of energy. And you can see that it's exactly the same as Santa Claus, my Santa Claus Jedicke experiment. We keep adding more and more energy into the protons, and the speed really doesn't change very much. It goes from being 99.9% of the speed of light to being 99.99999.5% of the speed of light. So where did all that energy go? Right? So we've injected 1 million units of energy into this proton, and the speed has not changed. So where did all the energy go? Well, you probably figured it out. The energy got converted into mass. The stationary proton, if a stationary proton has a mass with 1 unit, then that proton that's moving inside of the Fermilab accelerator has got a mass of 1 million units. So we've literally increased the mass of the proton by a factor of 1 million just by injecting energy into it. We converted energy into mass. So what I claim is that Fermilab is not really an accelerator. Fermilab is really a masserator. Now, what does this have to do with Santa Claus again? Let's bring it back to Santa Claus. So Santa's speed, as we already know, is 99.99999% of the speed of light. And at that speed, Santa's relativistic mass is 100 times Santa's rest mass. Now, Santa Claus probably weighs, he's a big guy, he's wearing a big bulky jacket. He probably weighs about the same as I do. So when he's traveling with his reindeer, he weighs 100 tons, okay, at nearly the speed of light. So this is actually only a problem when he's traveling at the speed with the reindeers. When he's actually landing on your roof, since he's stationary on your roof, he has just his rest mass. And so this means that you don't really have to worry about Santa Claus breaking through your roof, but you do have to worry about Santa Claus being clumsy when he lands. So let's talk about the third and final weird effect that happens at relativistic speeds. Let's talk about time dilation and also how we know it's true. So look at this interesting set of pictures here. Santa Claus, 1930 through 2005, okay? And you'll notice that Santa Claus does not look like he's aging, okay? So clearly, Santa Claus is doing something that's keeping him looking the same age. He is not aging very fast. So I want to talk a little bit about something that's often called the twin paradox. Now, I personally do not like the term twin paradox because it's not actually a paradox at all, okay? It's really like a twin story. It's a story about 2 twins that take trips in different ways. Let's say that there's one twin who's 5 years old, and she's a very adventurous twin, And she decides that she wants to participate in a space mission that goes out to a very distant star, a star that's 15 light years away. 15 light years means that the light from that star took 15 years to get here, traveling at the speed of light. And she's going to travel out to that star on a spaceship at the speed of light. So she's moving at the speed of light out to a star that's 15 light years away. It's going to take her 15 years to get there, and then it's going to take her 15 years to turn around and get back. Now her twin sister is going to stay back on the Earth. And she likes to just hang out at home, and she likes to get a good job and have a family. And so she's going to have a lot of fun here on the Earth. Well, if you could communicate, if the twin on the Earth could communicate with the twin on the spacecraft, and they could have a video of what the clock looked like on the spacecraft, you would see time going very, very slowly on the spacecraft. And in fact, you can see that time is barely changing. There you go. 1 second went by there. So when you're moving at very, very close to the speed of light, time slows down. Whereas the twin that stayed on the Earth, time for her moves at the normal rate that we're used to. And so after 30 years, when the twin that went on the spacecraft mission gets back, the twin is barely going to have aged at all. 30 years she's been gone, she's going to come back, and she's still going to be a 5-year-old girl. But the twin that stayed on the Earth, she's been aging at a normal rate, and so by the time 30 years goes by, she's an old woman of 35. Now this sounds very strange, right? This sounds like this is absolutely impossible, and how can scientists actually know this happens, right? And so what I want to show you with an example is that we actually can measure time dilation. We can actually see time slowing down for things that move very fast. And to do that, we need to know a little bit more about elementary particles. Now, I already talked to you, this is actually the full list of possible elementary particles. There's 16 particles here. I've already talked to you about 5 of them. And the only ones that really matter are those 5 that we already talked about, because they only make everything that we know in the universe is already made of those 5 particles. But these other 11 particles are interesting particles that play some role, but only in very esoteric situations. But one particularly esoteric and interesting particle is this one here called the muon. The muon is an interesting particle because if you just take if you just have a muon and you had it on a table or in space and you're just holding it, the muon would decay. It would just spontaneously destroy itself. Now, the details of this don't matter too much, but I'll just do it for those of you who may be interested. A muon decays into a muon neutrino, a W boson. The W boson then decays into an electron neutrino and electron. So the electron we recognize as one of our fundamental particles. These other ones are all sort of strange things that we haven't yet talked about. But it doesn't really matter what all happens here. The point to take away from this is that a stationary muon on a table in your hand is not going to last very long. In fact, it only lasts for 2/1000ths of a second. It means you cannot have these things lasting for any longer than 2/1000ths of a second. Now, if you had a muon that was traveling at the speed of light, well, in 2/1000ths of a second, at light speed, you only go half a mile. Now, just to put this also into perspective, light in 1/100000th of a second goes about 1 foot. That's kind of a nice, easy thing to remember. In 1/100000th of a second, light moves 1 foot. But at light speed, a muon in 2/1000ths of a second could only go half a mile. So now I want to tell you a little bit something called cosmic ray showers. Cosmic ray showers occur when something called a cosmic ray, which is one of these particles that's traveling, one of the particles we already talked about, traveling through space, and they've been traveling perhaps for millions of years, and all of a sudden they strike the upper level of our atmosphere. And when they strike the upper level of the atmosphere, they interact with other particles in the atmosphere, creating what we call a shower. Some of the particles travel all the way down to the surface of the Earth. Some of the particles interact in the atmosphere again and create more showers. And so this creates a cosmic ray shower, and this is a very schematic representation of what they look like. I wanted to show you a video made by some particle physicists at Fermilab showing what a real cosmic ray shower might look like if you were to look at it in detail. So this is a view zooming in or zooming away from Chicago, and you see the cosmic ray entering at the very top of the picture. The cosmic ray is constantly interacting with different particles in our atmosphere, creating a shower of other particles, and basically sort of punching a very high energy hole through our atmosphere until it strikes the Earth. So let's look at the schematic again, and I'll tell you that in advance that these red lines here represent muons. These muons are these particles that just last 2/1000ths of a second, and they should only be able to travel 1/2 mile before they decay. But in fact, what we know is that that is half a mile. And the speed, the height at which these interactions occur is 15 miles above the surface of the Earth. So somehow, these muons manage to last for 15 miles instead of just a half a mile that they should be able to travel. So they actually travel 30 times further than they're supposed to based upon their lifetime. So this is the indication that when these muons are created, they're traveling at the speed of light. These particles are actually traveling so fast that time slows down for these particles. And they last 30 times or even 100 times or 1,000 times longer than they should. And they can travel much, much further than the half a mile that they should if they were only traveling at the speed of light. So if we assume that Santa Claus is using the time dilation of relativity in order to stop or to slow down his aging process, right? And we know that from 1930 to 2005, he looks like he barely aged at all. We can extrapolate backwards in time, okay? And I did this extrapolation. I went back to 10,000 BC and dug out a picture of Santa Claus. He looks something like this. Very young-looking Santa Claus. So in the case of Einstein versus Santa, in which we're trying to determine whether or not Santa Claus needs to break the rules of relativity, I think I've shown you that Santa Claus does not need to break the rules of relativity, and Santa Claus is not guilty. But I want to also talk about something that's very interesting, that I've talked about relativity as being very bizarre, okay? And bizarre because it has nothing to do with anything that you're used to in your daily lives. But in fact, relativity is starting to play a role in all our lives right now. But relativity is not just bizarre. Relativity can be very practical. And the most obvious case, I think, for all of us is if maybe some of you are fans of using a GPS unit, measuring where you are at different times or going a hike. They rely upon these GPS satellites that travel above the surface of the Earth, that orbit the Earth. Those satellites move at 8,600 miles per hour. Now, 8,600 miles per hour isn't that fast compared to the 1 billion miles per hour that light moves at. But even though it's not so big, it still makes a difference of 38 millionths of a second each day on the clock on those spacecraft. If scientists, the people who designed these GPS satellites did not take into account relativity, then we would not be able to measure our position on the surface of the Earth to anything better than about 100 yards. But if you use a GPS unit, you know that you can actually measure your position to about 5 yards, or even better if you're very careful. And if it were not for the fact that we take into account relativity, we could not do that. So what they actually do is before they launch these satellites into space, they actually slow the clock down by 38 millionths of a second, so that when they launch it into orbit, it's moving 38 millionths of a second faster, and then it's in sync with spacecraft with clocks on the surface of the Earth. So relativity isn't just something that's bizarre and that scientists study and that we work on in laboratories looking at subatomic particles. Relativity is something that we use every single day. We use it whenever we fly. The pilots use GPS units to get from place to place. We use GPS units to go hiking. So relativity in our society right now is becoming so complicated that we cannot any longer ignore relativity. Relativity is part of our daily lives. Thank you very much.